Okay, let's go ahead and get started today. We're starting to run out of classes left in the semester, and unfortunately we're not going to get through everything that I wanted to get through, but we'll get through some of what I think are important things to get through. I want to get through HTTP and how that protocol works, and then I also want to move into at least some kind of game server programming. I want to get some web sockets in there too, which allows you to just like we did sockets programming, you can actually do that through a web page. So you could actually have something in your browser that opens a socket and either receives data or sends data. And so I wanted to get to that. I don't know if we're going to have time to do all that this semester because we only have really a couple classes left and then finals. But let's go ahead and get through this today. So HTTP is what we're talking about today, which is a specific use case of TCPIP programming. So what we want to do with HTTP, let's go ahead and move on here, that essentially we already talked about TCPIP being kind of the foundational protocol for the internet, meaning that everything that runs on the internet pretty much sits on top of TCPIP in some way. So that means that it should come as no surprise that includes web pages, web browsers, web servers that sit on top of that, and all of the other kind of associated web apps sit on top of TCP/IP. Now, in order for those, something like a web server, web browser to exist on the internet, it has to have its own protocol that uses TCP/IP. So in other words, it's going to use the transport services of TCP, it's going to use the routing services and addressing services of IP, and it's going to, on top of that, have this protocol that then uses the underlying reliable communication mechanism, routing mechanism, in order to send web page content from one place on the internet, a server, into a browser or client on the other end. So today we're going to look at how that protocol works from both sides, and we're going to actually look at a little bit of code that actually does that. So let's go ahead and get started here on that. So first off, HTTP is Hypertext Transfer Protocol, which the way when this is written out, it just looks like HTTP, but it's really, the other T is this text, so Hypertext Transfer Protocol, HTTP. And here are some dates on versions of it, version 1.0, 1989, 1.1, 1997, and then version 2.0, kind of 2014, adopted in 2015. So had a relatively recent update here, 5 years or so ago. But notice it's been around since '89, so it's been around for quite a while. So the major differences here between those different versions, 1.0 kind of uses a completely separate independent connection for every request and response. So in other words, if you went to a web page and it had images in it, you'd make one connection, you'd get the HTML content, the browser would notice, oh, there are images that I need to get. It would open a new connection back to that same server for every image. And if there were 10 images plus the HTML, you would end up with 11 total connection request response things. Now, 1.1, they added the ability to have one connection that you open, send a request, get a response, keep the connection open, send another request, get another response. And then for version 2.0, they added this kind of binary framing layer and multiplexed communication. So all at the same time, you could request multiple things through one connection and get those multiple things through that one connection. So rather than it being more like one at a time, you could say, okay, through channel 0 of this connection, get this picture, through channel 1, get this picture, and the kind of HTTP transport will sort that out and demultiplex it on the client end, multiplex it on the server end. And that kind of binary way of receiving those different pages and putting them back together is very similar to how sockets with port numbers works, but it's done kind of all through one socket and one port number where it has another layer of multiplexing inside of that. And we're not going to wade too deep into the weeds on how that works, but just know that those are the major differences. Okay, now the whole architecture is based on this client-server kind of model, meaning that the server, a web server, sits and listens for an incoming connection. When a connection gets made, then the sequence there, accept the connection, receive the request, send the response, and then Clearly, if you have the later versions, then there's a little more complexity that you could receive another request and another response on HTTP 1.1 and 2.0. You could actually send multiple requests and receive multiple responses kind of through this multiplexing system. But the idea is the same. Accept the connection. Once the connection is made, the server gets some kind of request for some piece of information. It sends a response, and that concludes that small transaction. Notice there are standard ports for this. Port 80 is the standard HTTP port. 443 is standard for HTTPS. But really, any IP port is possible. So you could have a web server running on any port that is set up to run a web server and handle this architecture. So these are the standard ones. So when you go to a website and you say, it's an HTTP website, and you say go to yahoo.com, it'll essentially try port 80. And what we're going to see later on is we can make our own services run on any port, and we can still connect to those from a browser. We just have to specify the port, because otherwise it'll default to 80 for HTTP, 443 for HTTPS. Now on the client side, the client is going to be the one that's going to kind of making the phone call, connecting to the server. Once it's connected, it sends a request, it receives a response, and then renders that in the browser in some way or does something with that resource that was sent to it. So relatively simple. It's just to kind of connect, send a request, get a response, do something with the data that you got back. Now, both the request and the response have their own kind of protocol format, and they're very similar to one another. The request and the response look very similar. And they're also human-oriented, meaning that it's not really in the default state this binary thing that is inscrutable. It's basically this human-oriented. In other words, if you were to look at the traffic, you could understand what the request looks like, what the response looks like. Now, both of them have this format. They have an initial line, which we're going to see more detail on that in a second. They have 0 or more header lines that follow the initial line. And then they have a blank line on a line by itself. In other words, just an empty line with nothing on it. And then a message body that follows that blank line. And that message body that follows that blank line is going to have file data. It's also optional. So, for example, a lot of requests don't have a message body, but you are required to have these things up here. Notice this is 0 or more header lines. So the minimum that you would need is an initial line and then that blank line by itself to say we're done with the header. And whether we have a message body or not, that's optional. All right, so let's take a look at the request side of this first. This would be what a web browser would send to a server. So the initial line for a request looks like this. It has a method and then a space and then a path to some sort of resource or what's called a URI. Or sometimes called, you can think of the URL as being, URI is part of the URL without the HTTP in the front. But notice this is some path to some resource that the server has access to. So this could be something really simple, notice it's just a string. And the string runs from that space up until the following space. So to parse this is relatively easy. Just say anything at the beginning is the method. Anything after the first space up to the second space is the path that we want to, of the resource we want to get. And then the third position here is the version of HTTP that we're using. And here this could be 1.0, 1.1, or 2.0, whatever, but this is specifying the version that we're making the request in. And the reason the version is right there in that initial line is that helps for new versions for how to parse this stuff, maybe treat the stuff differently. But in all versions of this initial line looks the same as this. All right, the next thing is we have 0 or more header lines that would follow this. So in our file, in our transmission, there would be no gap between this and this. It would basically, all of this would immediately follow the initial line. And so there can be these kind of headers, and the headers are always in the form of some kind of key, a colon, and then a space, and then some value that goes with that key. So here, this is an email address of who's connecting to that website trying to get this. This user agent might be what kind of browser engine they're using. The host might be what host that we're looking for this resource on. So this is not the person connecting here. One thing to notice is if you haven't configured it not to, is your browser could be pasting your email address in to any web page you visit. One other thing to keep in mind is remember when a connection is made over TCPIP and data comes in, that the receiving machine always gets the address of who's connecting to it. So they're going to get your IP address when you connect. They might also get an email if you have it configured to show that. Now, after the header lines, there's this blank carriage return line feed. And then after that, there's this message body, which on a request, like a GET, is usually empty. So on a GET request, there's no message body. We're not saying anything because everything that we're trying to get that tells what we're trying to get is right here. But if we were doing a different method like a post, we might be sending data up to the server, and then the message body would have some stuff in it. Now, a couple quick things to note over here is that HTTP 1.0 defines 16 of these possible header types, but none of them are required. In other words, at a minimum in HTTP 1.0, you could just say get, have the initial line, and then have the blank line, and that would be fine. In HTTP 1.1, though, if I say version 1.1, it defines 46 of these things, but only one of them is required, and the only one that's required is this host. And the reason for that is that allows HTTP 1.1 allowed kind of virtual hosts to be created. So in other words, I could have one server that's handling more than one website. So in this case, like garbageperson.com, you could have that running on this, or look for this resource on this host, or you could pass in a different URL like garbageman.com, and that would give you could give you a different resource than this request. So you're required to have the host on HTTP 1.1. But if not, all we need is the initial line and then the blank line, and everything else is kind of optional. All right, so moving on to the response. The response, it has an initial line too, and the initial line of that basically gives the version of the response, and then a status code, and then kind of a human readable version of that status code. So in other words, HTTP/1.0, 200, okay. Now, I have more spaces shown here just so I could space it out to put this on here, but usually there's just a single space, this, single space, and then the reason. So again, very easy. This is just a kind of ASCII text that comes across, very easy to look at, very easy to read, very human-oriented. Now, after that initial line, header lines, notice just like there was the user agent back here saying what browser it was or what rendering engine it was. Over here, we have what server it was that's serving it to us. It's often specified. Then there's some other ones that are usually there. Last modified, content type, content length. There are a whole lot of these that could be there. But notice this last modified, that could be useful for knowing whether or not that resource has changed since the last time you looked at it. The content type will tell us something about that. Is it an image or is it text? What kind of thing is it that's being sent in the body part of this? And then the content length is how many bytes long the message body itself is. So this content length does not include the blank line, just the message body afterwards. And that can be useful because it can tell the client machine, this is how much data you're about to receive until you have all of it. So usually you'll see at least these things being sent back as the response. But again, the browser will still handle this if these are not provided. But you should probably provide these. It'll even work if you don't specify the content type. The browser will try to figure out what the content type is automatically. All right, now the message body part of this, notice in this case I put something really simple there. Notice again, blank line, carriage return line feed on the line by itself. So in other words, there'll be a carriage return line feed that ends this line, and then another one, carriage return line feed immediately. Now the message body here, I just posted made a really simple message body that says hello world in bold. That'll show up in the browser. Okay, now a little bit more about those response codes. The response code, remember that's in this second position after the version. Those are all 3-digit codes, and they consist of the first digit determining the category of the response. It says error here, but it's not necessarily error. It could be not an error. So it's a category of the response. And we start off with the kind of 1 and then 2 digits after that. 1XX, so starting with a 1 of the first 3 digits is information, 2 is a success, 3 is a redirection to some other URL saying this thing's moved to here, 4 is an error on the client's part, meaning the client made an error, 5 is there's something wrong with the server has an error. So these have subcodes within them that we could look at. Now some common ones here, the second digit and third digit, those 2 digits together determine things. So notice 200 is a success and 00 is okay, everything went fine. Notice 404, which is an error probably some of you have seen before, all of you maybe have seen that before. That's something was not found. So that's in the 4 category, that was the error on the client's part. So notice they put the problem on you. You asked for something that didn't exist. That's your fault, not their fault for not having it. That's a client error, not a server error. But you might also see some other errors like 300 notices this thing's moved either permanently or temporarily. 500 is a server error. You make some request and the server has some problem. Yeah, sometimes you'll see that. And there are a lot of other codes you might see as well, but they're all divided up into these categories like this. Okay, now as far as the method, remember that's on a request, that's the first thing. We looked at a get. That's just to get a web page or a file or an image or some resource off a server. It could be a PDF or a zip file. It could be a lot of different things you can use get for. But that just basically says, I want that file. The server then, if it has that file, will then send it to you in its response. So that's what get does. But there's another one, head, that works just like get, but it only sends you the response header. In other words, you say, I want to get this file, it'll give you the file after the header. But if you say head of that file, it'll give you the response header, but not the actual body part of that. That will be blank. Now, why would you ever want to do that? Why would you want to get the information about a file or a resource, but not the actual resource? And one of the main uses of that is to see if a file has changed. Remember, it has that kind of last modified field that shows up in the header, or it has the size. Maybe you want to get the size and prepare for that. Maybe you want to look at when it last changed and decide whether, I already have that version, I'll leave it alone. But you can call this head thing, and I'll give you the header that usually will include last modified and content type and content length. So if you don't care about the data, just want to see if it's changed, head would allow you to do that. Now post allows us to send data from the client to the server. And that's usually when you're posting something or uploading something like post would work for that. Put is kind of creating a resource on the server, uploading a file and having it go the other way to put the data somewhere. And a lot of times servers will be configured not to handle that, so you just can't put things over that. Notice that when you put something, it could replace something that was already there if you have that location on the server set up to handle things. So you could upload files into that, but the server has to be written in such a way that's configured to handle that, and permissions need to be such that it allows it. So in other words, you can't just put things onto Google.com's homepage because you feel like it and have it replace what Google does. The server has to be set up to handle that. But there is something in the HTTP standard that allows that. Also delete. And again, delete the server has to be configured to allow certain things to be deleted in order to have that one work. And there are some other ones there too that I'm not going to mention right now. The main ones when you're browsing the internet would be get, maybe post, if you're interacting with something where you're uploading things or sending data to a website. Behind the scenes, it might use head for certain things. Okay. Now, one other feature of HTTP 1.1 that I should mention is kind of this chunked encoding that it allows on responses. And what chunked encoding is, it's a way to send more than one piece of data in chunks rather than as one entire message. And there's some advantages to that that I'll mention here quickly. And there's a lot of content here, but let me just kind of read through this. So chunked encoding, advantages of it are, number one, it allows the server to maintain that kind of persistent connection for dynamically generated content. In other words, there are pages that you say, hey, give me digits of pi, and it'll start filling up your browser, and it'll just keep filling it and filling it and filling it. Now, how do they have it so that the browser can start rendering it, and it'll kind of keep adding and adding and adding to it for that dynamically generated content? Well, it creates a connection, starts sending chunks of the data over, and once a chunk is received, the browser can start handling that while other chunks come in. So in that case, though we don't know the content length, so we can't put the content length header in the as a header, so we would leave it off. And then we would need to delimit the content in some way to say, I'm at the end of a group, I'm at the end of a group. And eventually, we want to say this is the last chunk and then be done with it. The second advantage of this is it allows us to send additional header fields after the message body. So in other words, you could start sending the data, and this is especially useful, again, for dynamically generated content, where it's not just a static file. So we don't know necessarily how much data there's going to be or what the content type is until we've started sending it, and maybe until we're done sending it. And then, so we can actually have some headers that show up. I would call them footers at that point, not headers, because header kind of implies it's at the top. But the concept is that we could send data, chunk the data, and then send that one of those delayed headers later on. Okay, for chunked encoding, the way that works, relatively straightforward. Essentially looking at that, the header will include the line transfer encoding chunked. That tells the browser that, hey, I'm going to start sending the data in chunks rather than in one whole unit like you're used to. And every chunk is going to have kind of the normal blank, following the normal blank line that you'd usually see. You'd have a line that has the size in kind of a hexadecimal string that specifies the number of bytes of that upcoming chunk. So we haven't received it yet, where we're saying this chunk is this number of bytes long. So for example, if it were the size were specified as FF, then we would know that we're going to get 255 bytes of memory for that chunk. And then that's going to end in a semicolon and then a carriage return line feed to put that. In other words, that number is going to be on a line by itself with the new line going to the next line after that. Now, the next thing we have is all of the data that goes with that chunk. In other words, this number of bytes of data. And that's going to be followed by, after that number of bytes, a carriage return line feed that moves us down to the next line. Now that gets us down to the next line. So that means we can have another chunk that follows that with another hexadecimal size carriage return line feed, and then another group of data, carriage return line feed. So that always puts essentially the reason for this carriage return line feed here is it always puts the next size on a line by itself without it being stuck on there with the data. So in other words, if we get a line with just a hex number, carriage return line feed at the end, semicolon, actually the semicolon you can leave off, it's optional. But the idea is hexadecimal number, carriage on a line by itself says this is how much data is going to follow. And you can have as many chunks like that as you want. So we can send more data, another chunk, another chunk. Eventually we have to tell the browser that that's the last chunk. The way that's done is you have a blank line here, go to the next line, and then with a size of 0 on it. So we'd have 0 semicolon carriage return line feed. Now after that kind of last chunk, you can then provide those additional footers or delayed headers. They are in the same form. They have a key, they have a value, and then the message is going to kind of end with kind of a blank line at the end, which is essentially the blank line that we would have at the end of 0 bytes. So 0 bytes of data, carriage return line feed, that blank line at the end is the 0 following the 0 bytes. So it's all very consistent, same format. All right, now, if we want to write a simple web server, it's really like writing any other TCPIP program, server-side program. And essentially what we need to do is once the connection's made, we just need to read the request. We know what the format of that looks like, maybe parse that, create, and then send a response to that. So as a reminder, thinking back to a couple lectures ago, here's how TCPIP programs, or server programs work. Essentially, we have to open a socket. We have to bind that socket to an address that we want to listen on. We have to listen. And then as connections come in, we need to accept them. Once a connection is accepted, we receive the request, we form the response, we send the response, and then close the connection. Now, this is kind of leaving out some of the details if we wanted to do chunked encoding or something like that. But this is like HTTP 1.0. This is what we would do. We open the connection, we do a receive, we parse the request, we fulfill the request, we send the response, and then we close the connection. And then notice at the bottom here, on a server where it's going to continue serving, it will go back up and accept the next connection. Now, in the real servers, what they'll do is they'll spawn off a thread to handle this exchanging data. So after the connection is accepted, spawn off a thread which frees the server to handle another connection at the same time. But a really simple version of this, we accept, receive, create a response, send the response, close that connection, and go back to accepting other ones. So in other words, think about this like somebody answers the phone. They say, yeah, what do you want? Okay, you want that. Here it is. Bye, and hang up. Okay, so let's look at the code for a simple web server, and then we're going to actually run that and test it. So let me, hold on a second, let me bring up that code. Okay, so let me switch over to the screen. All right, so here's the code for the web server. And let me go ahead and make the font size a little bigger here so you can see it more easily. Okay, so that should be a little bit easier to see even if you're on a smaller screen. Let me go a little bit bigger than that. There we go. Okay, so here's the code for a simple web server, and this is just going to be serve a static web page. In other words, it's not going to really get a file and send a HTML from a file from the file system. We're just going to send a static web page here. So the idea is this is in Windows, so I just have WinSock 2 and standard IO to print things. And then I define my server port with a pound define. It's a preprocessor directive, so anytime I see server port, I'm going to substitute 5454. And this is the port the server is going to be listening on. Now, we could change this if I didn't have a web server running on this computer. I could make that port 80, the standard port, and it would work the same way. But I'm going to do it on this alternate port here just so you can see how we would connect to that from a client, from a web browser. But essentially, a lot of this is the same as just stuff we saw before. So at the top here, initialize the WinSock, WSA startup. If that succeeds, then open a socket. If that succeeds, then the socket's created. Now set up the listening address. Now this here, I'm just using localhost. We could set this to use the address of the system we're on to make it public. I'm just going to use localhost here. And notice that's a AF_INET. And there's my port that I defined. That 5454 is right there. So in other words, I'm going to listen on this port on localhost. Now, moving on here, we have this well, I did a check of the address, but then I bind that address that I set to that socket that I open. And if I could bind, then I go down to here. The next thing I do is I do a listen on S with this backlog, which is defined by this SO max connections here. But you could, if you want to, just put a backlog in there, 5 or 1. In our case, we're only going to handle 1. But this, once I've been able to listen, now the socket is listening. It's now waiting for connections to come in. So when I hit accept here in my code, this server is going to, this server code is going to block and wait for somebody. So in other words, this says wait for the phone to ring. If it rings, answer it. And remember the way accept works is this is the listening socket. But when it answers that or connects, it gives me a new socket to actually perform the communication on. So in other words, the main line rings, we transfer it over to a new kind of extension to be handled. And the reason for that is that frees the server up to go back and accept other connections on the listening socket. And every time it'll spawn a new socket off when we answer the call. So that's how you can have a web server handle lots of traffic at once. It has one listening socket that when a connection comes in, spins it off into a new socket to handle that, usually in its own thread, and then that thread will handle that until it's complete, which frees up this to then accept and handle other ones. Now, once we get to here, that means connection is accepted, and this new _s variable is kind of the new socket we have. Now, all of that is the same as with any other TCPIP program. None of that has been different from the server we looked at in the past. Now, the part that's going to be different is now that we're connected, we now want to, we're the server, so we want to receive their request, which is essentially what we're doing here. Receive their request, which is going to be pulled into client request. And right now I'm kind of ignoring that request, but that request when it comes in will have the kind of initial line, the headers, the blank line. So if it's like get this thing, and that will run through and get that thing. But in my case, what I'm doing is I'm just have this static response. So no matter what they request, I'm going to send the same response back. So my response, notice the way that I've set that up is here's my initial line. I said HTTP 1.1, 200 OK. And then I have on the next line a couple of the headers, content type. And really, I don't even have the content length or anything. I just put the content type there. And then here's my blank line by itself. Let me kind of scroll over a little bit so you can see the rest of that. And then this is where the body of the response follows. So here I said it was text HTML. So here's the text, HTML, body, H1, hello. And H1 is just a header size 1 for your browser. Backslash H1 says that's the end of the header. And then there's the end of the body of the HTML. There's the end of the HTML. And there's kind of a new line at the end of that. But this whole thing here, actually including that new line at the end, that's the body of the message we're sending. So when we get this from a browser, we should see hello world in heading size 1. And if we wanted to, we could add some code here to center that or make it a different font or change the color of it, whatever we want to do. But you'll notice that I've created the response, pointed this pointer at that block of data, and now I'm just going to send it. And notice I'm sending it on the new socket that was created up here. So I received from that new one, I send my response. In other words, I receive the request, I send the response. There's the response that I'm sending. Here's the length of it. That's part of what we have to put to send. Notice I added +1, so it will also add the null character at the end and pass that along. This here was the flags, set that as 0. And then after we're done, we're just going to close the socket down. Now in a real server, I'd have a loop around this stuff to serve it multiple times. Right now, I'm just closing the whole program down when I do that. All right, so let's go ahead and see this thing in action and see it run. So let me go back to... All right, so there's the server running. So the server's running. Notice it said socket created, socket bound, socket listening. So that's all stuff that we just, so everything's up. And so my web server is now sitting on that. If we go back to this code, it's sitting on this accept line waiting for a connection. So let's give it an actual connection. So let me go to, let me find a web browser window here. Okay, and let me make this a little smaller so we can see it side by side with the server that was running. All right, so we want to connect to this server. And in order to do that, I'm going to put localhost, so 127.0.0.1. But then here, if I want to specify the port, I'm going to put colon 5454. And that is the, and let me go ahead and just put HTTP, or I have an extra dot there. So there's 5454. If I go to that, you'll notice the hello world shows up here, and my server closed because I didn't make it loop. But you'll notice that we got the hello world in the browser. And if I right click on this and say view page source, there's the string that was actually sent from my program to the web browser that shows up looking like this as the browser renders it. So you notice the web server, really pretty simple concept. So again, let's switch back to the source. So there's the source. Move this over a little bit. And let me go back to that code. That's not right. So here's the code. Again, notice here's the body of the HTML that was sent. And notice that there it is showing up in that. So if I were to change this text, the web browser would render something different. So again, HTTP, a pretty simple client-server protocol, and very human-oriented. It's very easy to look at that request, look at the response, and then see what you got. Now, HTTPS is just a secure socket layer version of that. So right now with HTTP, this message comes across unencrypted. So if somebody were to sniff the packets that were going across, they could see everything that was in there. HTTPS kind of encrypts that, adds an encryption layer, encrypts it, sends it, decrypts it. So very secure, because it negotiates a secure connection and then encrypts all the data. But the data that goes through that encrypted process and comes out the other end is the same as for HTTP. There's not really any difference in the way the requests and responses are made, other than that stuff gets encrypted from end to end. Okay, so let's quickly go back to the presentation here for a second. All right, so we looked at that code. Very simple. We ran it. We tested it with a web browser. So we did all those things. And we got that hello world that showed up in heading of size 1 when we went to that. So notice, to specify the port, we just put a colon after the address. If I put a slash and then some other information here, that would all show up in the kind of request when it came in on that initial line. Right now, what's on the initial line is just get space, just / because we didn't put anything here. So we'll just have a slash, and then kind of the version. And a couple notes on that server quickly, and then we'll be done for the day, is that it wouldn't be too difficult to add dynamic content. In other words, in that program that we had earlier, it'd be really easy to make that support dynamic content. It's just that message, rather than sending that string through, we could make it send through a fortune, or it also wouldn't be that difficult to make it. So it parses the URI out of that request and then looks for that file on the file system. And if it finds that file, then send that back as a response. It also would be fairly easy to get other information and put it into dynamic content, like for example, you could have it so it gets the I don't know, if we're on let's say we're on a Linux box, we could get the process table and post that as a web page, so you could see what processes we're running. You could do that remotely. We could also make it so that it would post who's currently logged into our server and post that as dynamic content. Or we can make it so that it kind of randomly picks a phrase from a file and posts that like a fortune that shows up every time we hit that website. Or it could be posts the time of day from the server. So there's all kinds of stuff we could do with dynamic content. In our case, we just said hello world and heading of type 1, but we could replace that hello world with anything we wanted, or even different files. Also notice it'd be really easy to send the contents of binary files in the body as well. It's not really any different than what we just did here. We could open the file, stick that in there like an image file or an executable or whatever we want to send through there, and it's designed to handle that. And that's essentially how all web servers work. They all kind of work that same way. Parse the request, send the response, and the browser then renders that. And notice that you don't really have to just serve files. You can make a web application. When you send this kind of request, it does this thing in the application and gives you this response back that does something. So you have like think of something, more complicated web application that allows you to like add calendar items and view your calendar, or something like Facebook that lets you upload pictures and then view them on that web page. That's essentially how all of those things work, is through HTTP on the back end doing that stuff. All right, so that's everything I was going to cover today. Look at the labs. There will be a couple more labs that are going to get posted this week. And then next week, I'm going to try to get some coverage in on how to make something like a game server. I know that's important to some people. So we're going to look at how UDP communication works, which is closely related to TCP. But as a reminder, UDP is kind of datagram oriented and unreliable. But for game servers, especially for real-time games, it's hard to beat because it's really fast. It doesn't have the overhead that TCP has associated with it. And for a real-time game, that's what we need. So we're going to look at that next time. So we'll probably have 2 more required labs, and then one that's going to be the game server lab that'll be kind of for bonus points. So go ahead and keep an eye on the page today for other things being posted. And other than that, stay safe. And we'll get through the last week here and then finals together. And hopefully things will start going back to normal soon. All right, so I hope everybody watched and listened. Stay safe, and hopefully I'll get to see you guys soon.